Hi there and welcome to this video for Senior Physics on Astrophysics. In this last video we're going to explore the idea of gravitational fields and how this has an effect the further out we go from the Earth's surface into space. So basically what we've got here is a representation of the Earth where we've got our gravitational fields which are centered into the center of the Earth. Now the thing is, what we need to experience or explore is what happens to a mass the further out we go from the Earth's surface. Now this makes pertinent sense when we deal with things like satellites and putting a satellite above the atmosphere and wanting it to actually circle the Earth. So what we notice is that the closer the lines are to the Earth, and you can see that right on the surface, the stronger the gravitational field is going to be against them. So you can see the further you go out, the wider the field lines go, which means you get a decrease in that gravitational field. So what we've got to understand is if we're going to put a satellite in space, we've got to work out what height are we going to do, and as a result, what is going to be the force of gravity which is going to apply upon it. Now, if you watched the previous video, we understood that we had to have a critical velocity which is required in order to get the satellite to actually move through space and keep it in a circular orbit. So it's important to know what's the strength of the force of gravity acting on that object at that specific height. So obviously, depending on the size of the planet, it will determine the size of the gravitational forces which are going to be applied upon it. The bigger the planet, the bigger the gravitational field. So our biggest planet in the solar system, Jupiter, is going to have field lines which are going to be a lot closer together. The Moon, however, doesn't have a specifically large gravitational field, basically because it's a lot smaller. As a result, the field lines are further apart, and that's why when we see photos and film of Neil Armstrong walking on the Moon, he's actually bouncing over it because the field lines are not grabbing hold of him as a mass and pulling him down as strongly as you would if you were on the surface of the Earth. So we can actually determine what's going on depending on the different planet surface. Now, obviously, if we're going to look at space exploration, we need to know what those gravitational fields are like. Now, here's a representation of a rocket, and you can see that relative to Earth, we've got a certain number of field lines. In this case, we've got 5 field lines acting on that Australian rocket there. Now, if we went to the Moon, we'll see that the number of field lines is going to be a lot less. We've got one from 5 to 3. So we can see that the gravitational force is less on the Moon than it is on the Earth, which means that we're going to spend more time in the air if we're jumping. But likewise, if we go to Jupiter, you can see that we've almost doubled the size of the number of magnetic field lines per specific area. So as a result, we can see that the gravitational field strength for Jupiter is going to be a lot larger than we're going to get on Earth. Now, obviously, we're only dealing with Earth at the moment, but the further you go out, what we're noticing is that those field lines are going to get further apart. So what we need to be able to do is to be able to calculate our gravitational field strength at any specific point. Now, our gravitational field strength, G, is the acceleration due to gravity on an object. Now, as we know, as we go further out, G is going to decrease. Currently on the surface of the planet, G is going to be 9.81 meters per second. But as we move away, that's going to get less and less and less. As we say, the bigger Fg is, the bigger the acceleration on an object. So we can't get any closer to the surface of to the center of the Earth. So the result is we're experiencing probably our maximum G, our maximum acceleration at this point in the atmosphere and on the surface of the Earth. But obviously, the further out we go beyond the atmosphere, G is going to decrease. That's why you almost feel weightless in space. As a result, we're going to decrease our field strength. This value can be calculated if we know the mass of the object in relation to the gravitational field. And it's done in the following way. Basically, we know that Fg equals gMe(m), where me is going to be the mass of the Earth and the little m is going to be the mass of the object relative to it. And that's all over the inverse square law with respect to distance from the object. Now that distance obviously will incorporate the radius of the Earth. We also know that a mass basically will have a weight force equaling mg. Now what we can do is we can combine both of these forces together, our gravitational force and our weight force. So we get Fg equals Fw. Now when we put the two equations together, we get Gme little m divided by d squared equals mg. Now we can cancel out our little m's, so that gets rid of the mass of the object relative to the Earth. So we now know that all we're going to be looking at here is what is the acceleration g based on the distance that we are from the Earth's surface. So remember, we've got our gravitational constant, that's our big G. We've got the mass of the Earth, which we know. All that's going to change is the distance that we are from the Earth's surface. So we get an equation which will allow us to work out gravitational field strength, G me divided by d squared. And that's the calculation that we're going to utilize along with our critical velocity to determine what velocity we've got to give for a satellite which is put in space at a specific height above the Earth's surface. So let's have a look at a quick example. Here we've got me. Now we've got a 1 kilogram mass which is centered on the surface of the Earth. Now the surface of the Earth is 6,400 kilometers, which is basically 6,400 times 10 to the 3 meters. Okay, that way we've got our we've taken it into our meters. We also know our gravitational constant. And as I say, we already know our mass. So we can work out on the surface of the Earth what the acceleration due to gravity is. So we can substitute it into our formula. 6.67 times 10 to the negative 11 is our G, our gravitational field constant. We've then got our mass, 6 times 10 to the 24 kilograms. That's the mass of the planet. And we've also got our diameter, which basically is our distance that we're going to be traveling, not our diameter, our distance that we are from the center of the Earth, which is 6.4 times 10 to the 6. Now, so that's our distance, and we're going to square that. What we find is when we put all that together, that 1 kilogram mass is going to experience an acceleration of 9.8 meters per second. So that's where our 9.81 came from. We were looking at the effect of a 1 kilogram mass acting on the surface of the Earth, which is 6,400 kilometers away from the center, with a gravitational constant of 6.67 times 10 to the negative 11. Now, what we notice is the further that we go out, we follow what's known as an inverse square law. And this was put forward by Newton. Now, literally what it shows is a graph that looks like this. So the further we go out, we basically square the distance, so we're going to actually decrease the amount of force which is going to be generated by 1 over d squared. And that's what the inverse square law means. Now, we've faced this in a variety of different things. When we looked at electromagnetic fields, when we were looking at electrostatics, we had exactly the same scenario. The further a charged particle went from another charged particle, the electric field strength actually decreased following this 1 over d squared rule. We also had exactly the same with electromagnetism. When we had magnetic field that was generated by either a magnet or a current carrying wire, the further we moved away from that object, it followed again the force or the the magnetic field strength decreased by 1 over d squared. So we follow this rule all the time. Now, basically, what we notice is that if we were to look at a variety of different situations from Earth's center, we can basically work out the size of the forces which are generated. So this table shows that. You can see in the middle column that if we were a distance 0 from the Earth's surface, we've got an acceleration of gravity by 9.81. Notice that our distance from the center is 6,400 kilometers. However, if we were to go and increase our distance, say let's go down to the very bottom, which is 13,590. So we're 13,590 off the surface. We've got to add to that the radius of the Earth, which is 6,400 kilometers. So that gives us a total distance of 19,990 from the Earth's center. Our acceleration due to gravity would only be 1 meters per second. That's actually less than what you find on the moon. So I hope you found that useful. Hopefully you can actually practice this a little further by doing some of the exercises that I've got linked to this post. So thanks for watching, and I look forward to meeting you again. Bye for now.